then SOC verification, right? So, so I will try to cover how things which are passing on our simulations and starts failing on the silicon, because majorly we have a normal conversations with the teams and everyone in the industry saying that, okay, first test chip or any product we brings in the market fails big time on the silicon, right? And that is every time a challenge for any product company or any company which delivers a silicon, and it starts failing on the testers or on the system process tests, right? So this is my disclaimers that I'm not sharing any internal information, and everything is like for presentation purpose and a kind of demo version or something. So, and I am requesting everyone to ask n number of questions, and I welcome, so that I can be interactive. And because when I will start going inside it, there will be a lot of questions coming in the mind of the participants, and they will not ask, then it might be possible that we are not reaching to the conclusion, or and understanding is not going in right direction, right? So I will present. I have presented a architecture, a normal SOC architecture, CPU based architecture here, right? So if you see this presentation, this snapshot I have taken from Google, uh, so you can see that this is the architecture where we have a processor, we have JTAG, PIOs, we have SRAM, voltage regulators, CAN, and everything, right? So this is a normal architecture looks like, right? So when we tape out, right, and silicon comes as a chip, right, to us, right? So it is very different than a normal SOC verification. So let us say when we are doing the SOC verification, we have all the waves and everything on Verdi dumped, right? So we can open anytime the Verdi or any tool we want to open and see the signals inside and see, okay, why my tests are passing and failing, right? These things we can check, right? But when the silicon comes, right, and we have just a few ports coming on the top level, right, and we as a silicon developers gets a lot of issues when we see that our chip is not working whereas it was passing on the test on the simulations, right? So if you want any question why this block is like this, you can ask any question. I will move forward based on this slides and try to bring a concept of silicon debug. So any questions? Why, you can ask why this block even exists in SOC, I can explain, right? Then only we can build a concept. No questions? Okay. So okay, so the biggest challenge is that when two blocks of any SOC interacts with each other, they stays inside the silicon or the substrate.
Hello?
Yes.
So slides are not changing.
No, I just came back to the same slide. I just wanted to speak something. Yeah. So here, let us see, there are 3 blocks. Let us say there is a JTAG block, ARM processor block, and voltage regulator block, and SRAM blocks, right? If you see, they are existing inside the same die.
So we make a slideshow mode. You have not made it full screen mode. Slideshow mode is you have not done. So
I have done it. I don't know why it is not coming. I have done it. So see,
okay. Then okay, fine.
It is not coming for you.
No, it's visible, but full screen is not visible. Like a slideshow mode, probably you have not done it. Is looks better.
We can browse through different windows by Alt tab. So you can come to the different screen. Actually, this is different screen. We have Alt plus tab.
So should I do something, or it will work?
Alt plus Sari is saying Alt plus tab. If you will press, probably it will look like the screen.
Okay, it is possible that my system has some security and some security is running in background.
No problem. Then okay. I think we should go ahead with this. No problem.
Right. Because I am doing it from my office laptop, and they might be having some restricted sharing and these things, right? Yeah. Okay. Please go. So see, if you can see here, there are two blocks. This is a JTAG block, this is a ARM block, and this is a voltage regulator and SRAM block. If we notice them, they all of them stay inside the same die, right? Die is same. And if we see that, let us say there is an interaction between the memory controller and the JTAG block, right? JTAG chain is there, or memory controller is talking with the SRAM, or it is talking with the flash memory. So these things are happening inside the same die, right? So if we see the clock to clock path, right? So from this path to this path, the skew, when we meet the timing, we do the STA, right? Prime time we runs and meet the timing. We see that the maximum, the TCQ path and everything we meet, and finds that, okay, when I'm sending some data on JTAG on this clock, it is made sure that data comes on the memory controller on the disk clock, or we put some pipelines also in between to meet the timings, right? So here we see this is the same die, and timing is already met, right? And skew is controlled, and a person who was meeting the timing, he has controlled the skews, everything is already met, right? So if you see that there is no issue when the blocks are interacting internally to each other, right? Because between ARM processor or voltage regulator or JTAG scan to ARM processor, everything is inside the same design. And skew is like when we meet the timing, we always takes the tolerance, right? Okay, we say that, okay, we are meeting the timing to 1 nanosecond, but let us assume that the time period is 0.7 nanoseconds, and we keep 0.3 nanoseconds for tolerance numbers. I'm just putting as dummy because it is not allowed to give the exact numbers. So we are going to like timing number of 0.79 second, right? Nanoseconds, and 0.3 nanoseconds we have kept for the tolerance, like what temperature moves or humidity moves or any PVT things happens in the world, right? In the external world, right? Or to our chip, right? Then also our timing is meeting, right? So the problem comes when we are interacting with the external world, these ports, right? So these are the ports which are interacting with the external world, right? So this, if you see, these are the ports which are talking with external world, right? And the problem is that if I want to connect my JTAG with another JTAG in another IP, another SoC, if you see, we can't maintain a flop to flop path, right? We are not able to maintain the flop to flop path, right? Because we don't know the trace length, right? So let us go to the next slide, right? So this is kind of I'm just trying to create a picture, right, where multiple SoCs are talking with each other, right? So this is a repeater, this is a computer, and this is Ethernet hub, and we are talking to each other. So let us say that this physical layer is sending some data to this computer, right? And as you assume that the data is launched with the help of a flip-flop, right? And this data is also being captured by a flip-flop, right? But you can assume that when we are having a system of any X company or Y company, these trace lengths can be different, right? If you go for to buy a laptop of any company, not quoting the names, but you can see that your USB port in one company is sitting on the left side, and USB port on another company is sitting on the right side, right? And the placements of processor is totally different, right? So if we are not able to do the timings and of these paths, right? Another is that even though we meet the timing, the wire is open. So these wires are open, right? Right. And so you can assume that this was a taped out by some X company, right? And like TSMC, Intel, a lot of companies do the silicon deliveries, right? So if you see, these wires are not on the same die. So the skew which this block is facing might be different, and this is covered inside a, this is encapsulated, right? So let us say that heating comes, right? So this wire will be first heated if the heating waves are coming from outside, and the internal chips will be heated later, right? You can say that the skew coming in these wires are different than the skews coming in internal to a die, internal to a die, and we have multiple dies sitting here, right? So this is the silicon behavior which we are majorly facing issues, because silicon is majorly facing failing on the testers and on the system boards, right? So this is the major issue which we are going to discuss here in the slides. If anyone has any doubt that why we are facing issues on silicon, we can discuss in detail. Please, I'm open to questions for the question for these two slides. Or I'm going little fast. You can tell me like I should be little slow. Any questions? No, okay. Okay, so I will try to explain what is difference between the physical layer and normal digital chip, right? So actually, I have already explained. Let us say this is our digital design, right? And we have any logic written, right? And this is a combo, right? And we have these flip flops, right? And when we meet the timing, we are meeting it the timing properly, right? And there is a challenge that when it goes other outside and talks with another IP or another SoC, we can't meet the timing on this path, right? So whenever we have this kind of issue, we have to put a physical layer, which makes sure that timing issues are not coming on these paths. And these are very analog specific designs. Digital design fails when our design interacts with the external world. So you can assume that let us say this is a data link layer of any PCI of a PCI IP, right? And a sequence of data is coming out, right? We are putting a physical layer. So physical layer is a concept itself, right? How physical layer is taking care that timing is meeting between these two ICs or SoCs, right? But we are putting the physical layer, right, which is majorly analog block, right? So one thing what we notice in the SoC simulations is that when we have a SoC and definitely a physical layer instantiated here, right, and it is a majorly analog block and interacting with the digital block. So you can say that in PCI Gen 6 we mainly have this is a PMD and this is a PMA. MA means analog and these digital, right? So this is a PCI block, right? So we can say that we are talking mainly with analog blocks. And when we verify on the system, we put a test bench here, right? And we try to model the behavior of nature, that what kind of temperature will come, what kind of variations will come, right? But modeling of nature is not practical, right? Any kind of surprise can happen anytime. So one kind of example I can take it like let us say you might have read in transmission lines in a chapter is there in BTech, right, where impedance calibration happens, right, where let us say impedance doesn't mismatch, then there are the reflections, right? And this is related to some waveguides, right? So we have the waveguides concept in BTech we have read, right? So we majorly see that, let us say this is a port whose resistance is or impedance is 100 ohm, right? And when we are connecting to the board or another IC and there is a 80 ohm resistance or impedance, right? And we are connecting to that. So we see that when data is being sent to it, because there is a resonance not happening and impedance is not matched, data is being reflected back to the same port, right? And data is not going inside. But in SoC verification, when we do the simulations, whatever we push inside with the help of the test bench, data goes in, right? So this is the one of the good scenario where we see that okay, our silicon verification fails but the passes, but the silicon fails, and our SoC verification fails to qualify the chip, right? So this is one of the problem, and there are thousands and tons of problems when we are interacting with the nature, and we want to debug them, right, when our silicon is on the board, right? So this is the one problem I have given, and this is a problem of statement where I will I will discuss to resolve that issues. And is there any other question you want to ask, right, related to physical layer? Any questions? No? Okay, so you might have seen when you do some Google or something, right? This CEOs of different companies gives a press conference when they comes with the new product, right? And people are looking at the gamings and these things, right? So they comes with NVIDIA press conference are very common, right? So they comes with saying that okay, this was our eye margin, this was our eye width, and this kind of things they see, right? So I have pasted few examples of eye margining and these things from Google, right? Google search, not from Google designs, right? So these are the few examples of eye margining in the physical layers. I will explain how things happen, right? So this is another example of PCI PHY transmission at TX level, right? This is an example of TX equalization, right? And so So let us go little bit deep and try to understand how this kind of eyes are coming in picture to understand the physical layer a little bit, right? So what happens, right? So this, let us say this is SOC and this is one more SOC, and they are trying to do the data transfer, right? And I'm just going very like little overview of that, not going into too much deep, because physical layer equalization itself a big topic which it takes like 5 to 6 hours to understand, right? So let us say I send a clock and I send a data, right? So this is the data and I'm sending some clocks, right? So when there was a physical layer, the clock was this and data was this, and this is the wire organized outside inside your CPU on your computer or something, or your laptop, right? You see that the trace length of your data bus, even though we keep them very near, we are working on nanometers and nanoseconds, right? So this trace lengths are different, right? So our data, it is source synchronous data we send, because our data is synchronous to the source, right? But when it is received by it is skewed. It is received like this. So a lot of skew is there, right? So this is, there is skew. And second problem is that when the skew is deterministic, we call it synchronous. And when skew is undeterministic, we calls it asynchronous, right? So there are techniques in physical layers which so let us say this clock is being sent here and data is being sent here. So there are analog blocks sitting here, which takes the data and the clock, right? So initially real data doesn't come. Initially it tries to train itself. This block of the design is trying to understand what is the trace length, what is the skew coming in. So what they will do, let us say data is fixed, right? And clock is this, right? And there is a skew coming. So the analog block will push the data this side and this side and try to see how many data is sampled properly. So this is a push of clocks, you can say. Clock is being pushed here, right? So if the design is trying to show that, let us say the design is, the clock is being pushed by the receiver by X amount of the skew, right? And vice versa also, in the negative direction also, it found that in this window, it was able to sample the data properly, right? So this is the eye, and how much the eye width is more, we are good at sampling the data, right? So we are trying to get the maximum eyes, right? But it is that definitely a challenge for us. If you see, this is again a copied from Google search. It is talking about picoseconds, right? So you can see how much small the eye is, right? You can say 80 to let us say it is something 180, 100 picoseconds, right? So the eye is very small. So it is very difficult for us working on Gen 6 and Gen 7 levels, right, to transfer the data, right? And even though at that level, when we are transferring the data and eye is very small, we are facing some silicon issues, right? It is very high, a very big issue for us to debug it, right? So, and this is analog block, right? So I was looking at the topics which we have covered in past. So people has discussed about ATPG and test patterns and these things, right? The problem is that ATPG and this test patterns works majorly on the digital blocks. Analog block doesn't give you access of putting the scan chains and these things, right? So it become again a challenge where our FIS is not the analog block is not allowing you to put the scan chains and these things, right? And then if there is some fabrication issue itself on the physical layer, right? And another example of physical layer is that, let us say this is a DDR, right? And DDR memory port is like 1000 ohm impedance. I'm giving a wrong example, so again, just for just knowledge of, right, not for exact numbers. So let us say DDR memory is 1000 ohm, right? And our the controller port is the PHY layer port is 800 ohm, right? So this PHY has capability to measure the memory, because memory is just a memory. It is not smart. But these days memories are also coming smart. Memories are coming with the IO buffers and these things which can also train to each other, right? But this SOC is trying to meet itself to 100 ohm. So it has capability to change its port impedance, right? And is trying to reach 1000 ohms, right? So we have written some logic of state machines and a lot of analog blocks in between so that we can reach to 1000 ohms, right? But on SOC verification level, let us assume that we verified it that it reached 2000 ohm, but in practical we see that 950 ohm is only reached, right? So there is a lot of reflections coming in, right? Then also that this chip, this eye width gets reduced, right? So these are the physical challenges coming on the silicon, right? Instead of SOC, because SOC is not a verification. SOC verification doesn't include this impedance and these things because it's just a simulation, right? But we can just model it out. And I have seen a lot of times that this models passes on the design verification, but it fails on the real silicon, right? And so, right? So this is timing and this impedance, one another example, right? So I have seen when we put the silicon coming out, we put on the board, right? So the first thing which the design team do is that sit with the silicon testing engineers and make the test and slopes ups, do the scan testing, do the MBIS testings, IOBIS testing, and then we go for the functional testing that our design is working as per the functional behavior or not, right? So what I have understood is that we have covered these topics till MBIS, I think, also in the previous discussions, right? People discussing about scan testing and these things, right? So majorly I am trying to cover functional testing, and then I am trying to cover the IOBIS little bit, right? If anyone has any question till now, I can address that so that we can move and understand the things, how we try to bring up the silicon.
So you are writing something, and these are not looking by. It's not visible to others because slide share screen is not visible to us. That is the issue faced by the participants.
Okay, so this is problem. Let me do something then. Okay. 1 minute. Okay, so let me close this. Now which screen you are able to see?
Yeah, screen is visible. Yes, yes.
Something changed actually. Okay. You can see the shared screen or the complete screen. Which screen you are looking? The one screen with no notes and letting something no notes. Next slide, and the complete screen. Which screen are you able to see now?
I'm able to see your PowerPoint presentation, and it is not full screen. A cursor
Okay.
is also visible to us.
Okay. Hide presenters view. Now you can see. I hidden the presenters view. I think you presenters view were getting shared. Is it coming now properly?
Yeah, it's the same. It's the same.
I think then it is a security feature of Synopsys, I think. So presenter view screen.
Just try Alt tab. Press
Okay.
Alt and tab.
Alt tab I am pressing.
No, keep pressing Alt and tab one by one. So you will browse through many windows.
Okay.
Or maybe you have shared only window. You have to reshare it.
Actually, complete laptop is not allowed to share. That's I tried in
Oh,
beginning, right?
Okay.
So let
No
me
problem.
share it.
No problem. Go ahead.
Let me try
It's
again.
visible
Stop
anyway.
sharing.
Maybe you can go ahead with the same. Yeah.
Give me a second. Actually, I should have done it from my office. I was not expecting this. I should have done it from my personal laptop.
Just share screen actually. Just share
Yeah,
screen.
yeah. I'm just trying. Yeah, I'm trying it again. Yes. Give a second.
Share the entire screen instead of a
Go
single
ahead.
image.
No problem.
Right. Let me try
worry
it.
about it.
Yeah, let me try it. If it is possible, I will do it. In meanwhile, people, if somebody has some questions, we can cover that. Actually, when I am sharing the complete screen, a check starts running. Okay, it came. Okay.
Yeah, now it is fine. Now it is working, I believe.
Right. Okay.
So yeah, it is best. Now it is good. Now
Right.
it will look like.
Right.
Okay, thank you.
Sure. Thank you. Sorry, actually, this was some internal check by Synopsys. Okay.
So if somebody is having any questions, please feel free to type in the chat box. We will take the questions later.
Sure. Okay. Okay, so I'm not covering these topics because I'm assuming that these are covered in previous discussions, right? So I'm prepared with dive-based and functional testing, right? And let us go a little bit, right? So this is an example of a file layer, right? So if you see, these are the two paths, and which is you can say is like kind of this is actually file. This is the file, right? This is actually file. If you can see my pen, and this is the clock recovery and this thing. This again, this is a digital block, right? This is again a digital block, and this is a file layer. Phi is made of digital analog both, but this is mainly analog. And till this, we can say this is a phi. This is a physical layer, and this is going towards the controller layer, and this is a controller layer. This is a controller, right? So now let us say we has a SOC and we have a PCI slots here. We have a PCI slot or DDR slots, and silicon comes, right, and we put it on the board, and then we see that that our PCI is not working or DDR is not working at all, right? So and you see these are the analog blocks. We in these blocks we can't have the ATPG and scan resolution options also. So we, because these are majorly analog blocks, right? So inside that blocks we can search a digital block and put some ATPG, but majorly these are analog blocks don't allow to put the scan chains inside themselves, right? So we put the chip and starts failing, right? And then we see that what can be done, because anything outside the world is affecting this fail. So our first prediction is that my chip is good, but something at the port level is good, not good, because we are interacting first time with the physical world, right? And our ports impedance and some timing are breaking at this level, at this port level, right? So so we, how can we find out, right, that which thing is not working fine, right? So what we do, we have a kind of logic called IO based loops, right? IO based loops, right? So what we do, built in self test, this is self test, so everyone knows it, right? So what we do, when we go deep towards the ports, we are going towards the problems, right? Because we are going to handle the physical world, right? So what they do, so as soon as silicon fails, we have a overrides here. So we can say that this is a path. Let us say this is a FIFO, right? And data is being flown to this FIFO and then going to 10B, 8B, 10B decoding, encoding logic, right? So where we put a mux here. So we put a mux here, right? Like this, right? And we have a controller here, right? And what we can do, we take this input and we can put a decoder also here, right? And we can put it like this. Okay. So when we put a mux, right? We put a mux and enable the, so let us put a mux here and make it enable. So what happens, right? This is a functional path, and this is a IO-based path, and this paths get activated through this way, right? So if this, the design flows, the data flows through this. So this, you can assume this. So for the same PCI, this is lane 1 or link 1. This is PCI of lane 2, or we can say link 2. We are saying that this is a x4 configuration, right? For 4 lanes, right? So this is link 1 and link 2. So we make the first link as a transmitter and second link as a receiver, and we just make the loop back data like this, and we see the data is being received properly, right? When we see the data is being received properly, it means that our core pack is working fine, DMA bus is working fine, packet generation is working fine, FIFOs are working fine, and these are all the digital logics, right? Definitely we don't face the issues here, right? Majorly we see that if we are passing the digital loopbacks, majorly we pass them, right? So and after that, when we pass it, next step of the engineer is that, okay, let me disable this loopback, and with the help of JTAG, I can explain the JTAG also in the detail, due to limitation of the time, how JTAG works and why JTAG. Why only JTAG? I am saying JTAG override, not other override. That is again a point of discussion. So we have a JTAG overrides which control the muxes, right, and tells that, okay, now you create a one more loopback, the data flows like this. And this is not a ATPG path. This is a functional path, right? So we are just enabling the different paths, right? And we see that silicon is working fine till 8-bit decoded. Like, let us say the data came like till FIFO, it converted to coding happens, and here decoding happens, and data is being received. It means that this decoder is working also fine, right? Now, after that, we will create a next more loop back, which will see that this port will be connected directly to this port, like port-wise connection. We are going to the external world, but we are not connecting it with the tester. We are not connecting with the another IP or another chip. We are just connecting to our chip, because we are belonging to the same family of the same die of same fabrication team, right? So it is possible that if my resistance is 1000 ohm impedance, then it is also expecting RX also expecting 1000 ohm impedance, right? Let us say there is a fabrication issue and both face the same issue, so the fabrication make it 900 ohm and 900 ohm, and both of them matched, and the data gets transferred. And other analog issues we can see, right? So we see that, okay, data comes like that, the data is being received properly like this, right? So we can say, okay, there is something which is breaking at this level. Means the external IP, external SOC, or external tester, because many times we drive the data from the tester also, from the CR or these things, right? We see that something is bad from the data which is being pushed out, right? So, okay, let me take a very good example. I have faced like 6 to 7 years back, right? So I'm not quoting the name of the company and these things exactly. What was happened that we were bringing up some SOC, right? This was SOC, and this was a port, right? And this was a tester. This was a tester, and there was a resistance connected to it, and it was connected to VDD like that. There was a terminal, uh, one word called resistance, right? So I forgot the exact name. So what happens, right? It was like 400 ohm. Again, a dummy example. It was not 400 ohm, and we were connecting with with the external resistance on the board, testing board, and it was something 380. But because it was coming from outside, from the tester company, right? Because we are a company which delivers SOC, and we are buying the testers from outside, right, and putting our SOC on it, right? And we mainly read the spec of this tester when we check pass our SOCs there. We read the specs there, right? So we read the spec, right, and it was by mistake written as 400 ohm, and it was my blog, right? I was very unlucky, right? And it was my blog. It was complete SOC, and complete SOC was bring up done, right? So ready to deliver, right? And a lot of press conference happened that we are going to deliver this chip and this date and that date, right? But my blog was not coming up, right? So uh, we checked it, right, at that we read the spec many times and say, okay, impedance is not an issue, this thing not issue, everything is fine. So it's like 1 month delay, right, we were facing. So suddenly one of our senior, that time I was very junior, one of our senior came and so, okay, bring your multimeter, right? So, and that person bring a multimeter and ask the tester team, right, can you check the resistance? And we got it 380 ohm, and again a dummy number. And we, oh, this tester company has given us a tester board which has the resistance wrong value uh, there, but like no, as not per the spec, right? And we are 1 month delayed, right? And as soon as we complained with the tester team, then they changed this resistor, right? And our chip got bought up in a single day, right? So this kind of things we face, right? And how we debug them, right? So this is a challenge we can see here, right? So this is IO based. I was explaining, like, this is the reason IO based, with the help of IO based, we can make our things narrower, right? That, like, here we have made sure that FIFOs are working fine, package is working fine, decoding is working fine, as serial to parallel is working fine, clock recovery is happening fine. Only RX things are wrong or TX things are wrong. This kind of things we can check, right? Or we can do one more thing, like, let us say it is a problem that our transmitter is working fine, receiver is not good. So we can say that, okay, then also test fails. So what we can do, we can put dummy tester receivers and send the data, right, and it is being properly received by the tester, we can say that, okay, this path is clean, and then we put a tester and sends the data not from here, and it goes here, right, and say that, okay, receiver path is not good, right? So that kind of things we can do with the IOBest, and there are a lot of techniques we have things, and again trace things, and these things we can discuss in detail, and in future we get the opportunity. So okay, let me go in design for debug, and when I started working in industry, and when we are working in today in industry, a lot of things are changed, right? So let us say there is a JTAG chain, or let me pick a simple USB device, right? So this is a block. So this is a block. I have seen like 10 years back when we were working, every company was developing their own IPs, right? So let us say you are working in a company A, and you are getting the IP from the same company A, right? And you want to add some DFD logic, not design, DFD, design for debug. You want to add, right? Then because we are working in the same company, we can anytime request the USB team, or we of the same company, or we can do ourselves. We can put some test logics inside it, right? But the challenge is that with time, people realize that, okay, we are doing the repetition, right? That we have to uh, use a USB device or USB block inside the SoC. Let us not develop it ourselves, buy some from IP companies, right? Like we Synopsys delivers us every SoC IP in the market, right? We are not majorly, we have a lot of big market delivering the IPs, right? And almost every company in the world buys our IPs, right? So you see, the industry changed in last 10 years, where we started from the freedom of doing our debug hooks inside the blocks, whereas now the IPs are coming from the vendors anywhere, right? And now the freedom of SOC developer is gone, because we can't touch, or we are not allowed to touch the the internal IP. Let us say we are working a company A, and buys a IP from company B, right? And suddenly we say that we need a debug hook at SOC level. We have a requirement, right? And we decided to add some RTL logic inside the block, which is given by vendor B. And when it fails, the vendor B will, if there is a silicon debug, if there is a functional bug inside that in the block B, he will not own any responsibility, saying that, okay, you have touched it. You just put a comma, or you put a comment in my area. I don't own it. You have to use exactly. Let us say there are RTL files in any block, right? And you just went inside in any of the block, and you are not doing any RTL change. You are not doing any logical change. You just put a comment there, slash comment, right? And then you synthesize it, and the chip got taped out, and the silicon stopped working. And then somehow the vendor B will say that, okay, see, you have edited it. I don't own the responsibility. So that's how the industry works, right? So we are not allowed to edit the blocks, right? So this was the conventional way when we were allowed to go inside, because I have seen that we were putting a lot of debug hooks inside the design. But now I have seen that we are our hands tied, because we are not allowed to touch the IPs, right? So now the next challenge came. So what we can do, so that we can get the data from the IP on the outside to debug it, and that these people will not complain also that we have touched their IPs, and we have broken their sanity, right? So this is a next challenge we are facing in the design for debugs, right? And this is a change I have seen in majorly in last 5 to 6 years, where every company is working to optimize their business and not spending duplicate works and these things, right? So when I am proposing like a very small solution, like this is an example, and this is not a product example, not used anywhere. So this is a block where we are trying to get the data outside from the silicon, right? And try to debug it, right? So what happens, right here, this is a block, and this is a mainly a software block, and these names are again dummy, doesn't make any sense, right? So this is a software block, right? What happens, right? This is a your RTL design, right? And there are tools. Again, I can't go in deep and how the tool works, but this tool, there is a tool which can read this RTL, right, and understand what should be the behavior of this design, right, and we fit to it, right? And this is a tool outside, not on the SoC. This is a tester equipment, right? And it gets the data which is being sent. This is all the logic developed for design for debug, right? And it comes out and it compares. Okay, it will, oh, this A controller is buggy, right? So what will happen, right? I will little bit explain this code, right? What is happening here? So this is a software, right? And this software is sending. So first of all, again, one more logic is that if we the security block, let me go a little bit talk about the security also. Let us say this is SoC, and in SoC there is a CPU, right? And there is some logic which can go deep inside, right, and read the instruction sets and the data registers inside. Then it is a hacking mechanism. Anyone can go and read the instructions and everything. If you're doing some banking transactions and everything, then CPU can be read in parallel with the CPU can be read in parallel with the real transactions happening, right? So whenever we go inside the CPU or any SoC, before entering the debug mode, we have to put a security mode. And the security mode keys, or the magical keys you can see, are only owned by those SoC company developers, right? And they only do the debug, and after debug and every silicon is clean, then only they sell to the market. So means these keys are, and the security blocks and these encryption blocks are black box for the vendors, right? Right, we debug it and we give you, right? So the interaction of the software goes to the security block. This is very specific to me. I put in the software that lock key, and it goes and first unlocks it, right? When it unlocks it, it goes into the in a form of a 4 wire transaction. And again, you can see there should be question. I am expecting that why I'm not bringing HB APB outside, and why JTAG, and I'm expecting this kind of questions in the later stages, right? So the JTAG will unblock the security, go in the interconnects, and then go to the processing engine. I have put it P, but mainly it is a CPU. I'm just trying to hide the names exactly. And so it is a processing element, right? So processing element will go inside the fabric. Again, fabric. There are a lot of fabrics, right? Industry, like NVIDIA gives the name fabric called NVLink. uh, ARM has a fabric called CMN, and like there is a very big competition of making optimized fabric, because maximum delay is being consumed here, right? So this JTAG talk to the P goes to the fabric, and fabrics talk to the controller. The A controller might be DDR controller, HBM controller, any kind of controller. And see, this data is coming out, debug data is coming out, and we have a trace funnels, bring to the trace buffers, and processing element takes it and put to the RTT sequencer and gives us software, and software compares it. Okay, sequence is broken, means we are debugging it outside. So it is very tricky logic we have to put it, right? When this is like DFT architecture itself is a very tricky. So let us say this is a very big block. B block is very big, and it contains 1 lakh of nodes, right? And at any time event, there is a buggy event comes in, right? So so it is very hard to tap that event at that moment. So let me give an example of yesterday I faced, right? I was driving outside, and I was feeling that when I was pressing the brake sometime, my ABS was unnecessarily getting activated, right? And my brakes were like bypass kind of stuff. I was facing that issue. But when I and like it is one time out of thousands, right? This kind of scenario I'm facing. But I when I to go to the company and say service center, they try to put the brake, and brake is working, right? And so we are not able to catch that event, because that is all electronics, right? So it is a responsibility of the debug architecture to sample the event, right? How we will sample the event, right? how will we trigger the event? So these are all architectures level of things we have to think, right? And then these triggers will go through the fabric to the controller, and then they will come to the trace funnels and comes outside, right? So this again is a deep part we can discuss again in futures if you will interact, right? That how we send the events and how we are sure that the events are happening at that time when we need the data. If it is possible that a bug come and it got bypassed, right, and uh, bypassed, and later we are sampling the error statuses through the stress funnels, and it is showing, oh, everything is passing, but the event is gone, because it is a processing element. You are doing sending the instruction, and like every moment of second and every clock we are getting lakhs of nodes of data being generated internally, right? So it is a very big challenge for us, right? Like one example we will take, right, that there was a aeroplane accident, right, where people were discussing with fuel disabled, right? So why there was no state machine which should have checked the height and bypass the disabling feature of the fuel, right? There should have some test. There should be a logic inside. Was that logic failed, or I'm not questioning anyone's capability, but like this is like, okay, I have sensor that I have sensor at which height I am, right? What is my speed? And okay, who did this? The oil, the channel closed, right? But what were the sensors doing, right? Why that button was not bypassed, detecting the these things. So this is kind of all the DFD architectures on functional safety architectures, we can say. This is more majorly a functional safety architecture, right? So this kind of things we are doing in DFD, right? And this is like a more deep infrastructure of when we are thinking about the risk files, right? Where these are the instruction blocks, and we go and captures the events of every CPU instruction, right? And this is just uh, just a overview I'm just giving, right? How, what kind of challenges we are getting on the real SoC silicons. So okay, so this is just like I copied from ARM site. Again, it is a freeware, right? And I'm just trying to show, right, that on they have developed some core site architectures, right? And they have given their these kind of informations on their website. It is free. That's why I'm sharing, right? So if you see, they have given that much number of debug hooks on the designs, and they are giving the IPs, debug IPs, and people are using them, right? I'm not talking about synopsis, not allowed, only freewares allowed, right? So okay. And one more thing, okay, so here I talked about some software. So where we are having one more kind of software debugs, like called trace 32 and other trace debug softwares are there, right? So this was the basic overview of the silicon challenges we are having, and how much RTL, how much architecture we are putting in it to just debug the silicon, right? And one more thing I was not able to add in the slides was that we have always a limit, right? That the defect DFT architecture area should not be more than 10% or some number, right? That is again not quoting the right number, but some 10%, 15% of the functional area, right? So that is a limitation, right? We can't put n number of designs inside it. May see that, okay, I have put 100 flops for the functional design, and I put a 50 flops for design debug only, right? And with 150 flops in the design, so no one is going to buy the design, because the design's area is like increased very exponentially, right? So this is another challenge, that every time a DFD architect thinks upon adding some block, every time he has to think, okay, I am redundant, I am just only useful when we are bringing up the silicon first time, right? And when the silicon, the chip is qualified, then there is no use, right? Might be in functional safety we have use, right? The like aeroplanes, when the plane is turned on, we see a sound called e, like that, and this is IOBIST running in inside, right? Checking all the parts again every time it starts, right? So that is again reusable, right? But majorly the DFD blocks are redundant after first qualification, right? So we have to think upon the area consumption also, that we can't bring the area out of our boxes. So I'm running out of the time, I think. Yeah. So yeah, I'm done with my today's discussion, right? So please, I'm open for the questions you want to ask.
Thank you so much, sir. There is a question in the chat box. Dr.
Okay.
Aditya Mandlo
Yes.
is asking at every time,
Yes.
how we select among various testing methods and which one is the suitable, most suitable one.
Okay, so I'm just going to the question. Okay, I'm able to looking understand. Whatever. At every step we apply scan chain. How we select among various testing methods. Okay, so scan chain is not a DFT debug logic. Scan chain is only for testing the silicon fabrication issue. So let me explain that. That is a very important topic I should cover. So I assume that this is covered, right? So okay. So yes. Okay. Okay. So there is a difference between DFT and DFD. DFT is designed for testing. This DFT is designed for debug, right? So what is DFT? So let us say that we have a chip, or this is a combo. This is a NOT gate, right? And then there is again a combo, and this is a, just I'm putting a NOT gate to analyze this, right? And this is a complete SOC. This is 4 flops on, right? And when I am fabricating it, and you see when we fabricate it, we see the VDD rails and metal layers and everything running out right around, right? So what happened, right? This is my logical layer. This is a logical layer of data path, you can say, and this is a VDD path, right? And because they were very near, you see that there is a bulging out of fabrication time. There is a bulging out of the VDD layer, right? And we see that there are two cases that this line is very near to it. So let us, this is a flop. This is a flop, and I have I have met the timing on the simulations. I was not aware that fabrication will do this kind of gocha, right? Then what will happen, right? I made the timing saying that when data will be launched here and it will be captured here. So let us say the data is going from 1 to 0. Transition is going from 1 to 0. So in normal behavior, this path, this wire delay might be like 20 picosecond, and data is being going from 1 to 0. So let us say this is 1 nanosecond time period, 1 gig clock. So when one is data is going to 1 to 0, the real data will go here low, right? Transition here, this charges, and we gets the data here low, right? This is the real expectation. What happened, right? The VDD line passed nearby, and this line, by magnetic interference, or you can say disturbances, I'm not deep of this characterization things, I'm an article designer, but what I know that there is a disturbance due to that, which can pull this line towards VDD, right? So it is possible that it is either shorted, it can never go low. This is called stuck fault. When it is so if you will see there is a terminology in ATPG scan chain, we say stuck fault, right? So when stuck fault is there, this is connected to 1 and it will never go 0, right? Second case is that uh, it became slow at when we are bringing 0 to high, it is very fast because it is already influenced by VDD. But when I'm going 1 to 0, it is influenced by VDD and it is not allowing to go down. So it is possible that instead of going down here, it is going down here. So it is timing is like violated here, right? So this chip will not work, right? So okay, so how ATP scan chain works here, right? So what they do, so let us say we put a mux here, right? We put a mux everywhere. We put a mux. We put a mux here. These are the muxes we are putting, right? And these are all scan enables. This is a scan enable port, scan in, and this is, let us say, this is a scan I mode, right? This is a scan mode, right? So when, let us say, let me make it little a wave diagram, or let me, how can I clear it? Okay, this is okay. So this is a clock, and I want to judge it that this is not this is this fabrication issue is not there, right? So what I will do, is that I will put my scan enable high for 2 cycles and put here 0, So if I will put it 0, it becomes 0. Yes, I'll put it 0. So scan in value will be 0, going like this. So you see, scan enable is high, first clock will come, this 0 will reach here, right? And next clock, this 0 will reach here. But the problem is that this is affected by VDD, right? And it is tied to 1. It is stuck to 1. So it will never become to 0, right? And then I will put scan 0, scan enable 0. So what is expected when I scan enable 0, data path will be, so this is like a scan chain, right? These are the scan chain, right? So when scan enables go 0, it will go through this path, right? So the expectation is that when this 0 0 is there, inverter will make it 1. So this data will become 1 here. And then again, scan enable will go down, scan enable will go high, and data will be shifted out, right? So 1 will be shifted out. So 1 after 2 clocks, I will receive a 1, right? But here, if you see, instead of data being received 1, I received 0, right? Then we can judge it that some node, and there is techniques how to know which node is tied, which node is affected by the parasitic capacitance and these things. So we can tell that this silicon will not work because our mask or fabrication machines who is fabricating the chip has some bug, right? So that time we will say that this is a silicon fail. We have to throw it. That's why I gave the steps. So I give the step. Scan first, put the clocks up, then scan testing. If scan testing is failed, then we have to throw the chip. Another thing is that, let us say it was not actually stuck, it was affected by it, it made the design slow. Then we can sell still in the market saying that, okay, our design was designed for 1 gigahertz, I am selling it in for 200 megahertz, so I'm cheap, I can sell it for a cheap products, right? Like I have, there is another examples, I should not quote it. So okay, so 200 megahertz we will go and sell the chip, right? Silicon testing, scan chain is not for debug, but there is a corner case. Where we use the scan dumps for uh, do the debug also, right? What we do, that also I can try to explain. uh, it is it's not working. Laser is not working. Okay, it's little slow. So what happens, right? That let us say this is a CPU and we want to debug it. There is some issue, right? So what we'll do, we will bring the CPU in scan mode, right? And stops the clock, freeze the clock at that event. But this is again a debug mode, because scan testing don't have an option of freezing the clock and tracing it, right? So what we do, we freeze the clock. And let us say these are the flops, right? Or these are the flops, and these are scan muxes and scan chains and these things, right? So I freezed it. So I have every value here, right? And I will put all the values in a big SRAM and bring it through the JTAG or anything, or trace bus or anything. But again, we are using scan chain for a little bit helping us to debug it. But scan chains are majorly to catch the manufacturing defects, not for functional silicon validation. Am I able to answer the question?
Thank you so much, sir. I hope, Dr. Mandloy, it is the answer to your question.
Yeah.
If there is any other question, please feel free to ask. Otherwise, we are going to conclude it.
Yes. So for each chip we do IOBIST, it depends, right? It depends upon the criticality. Majorly, if you have PCI, DDR, or big SoCs there, right, and we have chances that at physical layer we can break something, right? We need IOBIST. Or okay, at functional level, right? You are talking that yes, FUSA chips. I think IOBIST is always there, which goes in automotive right? And on the aeroplanes and these automotives like your car, cruise control and these things, we always should have IO based, right? Big companies like I don't know, it depends, right? If a chip is FUSA and fuse functional safety enabled, it should have IO based or a parallel mechanism which works like IO based. Yes.
Thank you so much, sir, for your insightful lecture. I have noticed that you have covered a lot of things which are really very relevant, and these are connecting the digital RTL design and the testing in today's perspective and its FDP's perspective. So thank you so much, sir, for your insightful. Thank you so much, sir.
Thank you,
So,
ma'am.
dear participants, with this, we are going to conclude this session, and we will have our last session in evening 6 p.m. Thank you.
Thank you, everyone. Thank you, sir. Thank you, ma'am. Bye.
Sir, have a nice day. Thank you.
Same to you, ma'am. Bye.